Why nature refuses perfect symmetry. At first glance, the universe looks balanced. Left mirrors right. Action meets reaction. Everything feels fair. But beneath that appearance lies a quiet rebellion. Nature does not fully respect symmetry. It allows it, flirts with it, then breaks it in subtle, irreversible ways. And that refusal is the reason anything interesting exists at all. The universe presents itself as orderly and balanced, yet this presentation is misleading. Beneath the surface patterns that suggest harmony and equilibrium, there exists a fundamental tendency toward asymmetry that defines the very structure of reality. Without this breaking of perfect balance, the cosmos would remain frozen in a state of uniform simplicity, incapable of producing the rich complexity that characterizes our observable universe. To understand why this matters today, we need to revisit why symmetry felt so important in the first place. Symmetry promised simplicity. If the universe behaved the same forward and backward, left and right, past and future, then its rules would be elegant and complete. Early physics leaned heavily on this idea. Symmetry meant conservation, predictability, control. The appeal of symmetry was both aesthetic and practical. Mathematically, symmetric systems are easier to analyze, their behavior more readily predictable. Philosophically, symmetry suggested an underlying perfection to nature, a cosmic justice where no direction or orientation was privileged over another. Scientists found that symmetric principles led to conservation laws that governed everything from energy to momentum. The more symmetric a system appeared, the more fundamental it seemed. This created a powerful expectation that the deepest laws of nature would exhibit perfect symmetry, that any apparent asymmetry was merely superficial, waiting to be resolved by deeper understanding. For a long time, this belief seemed justified. The equations worked. Experiments agreed. Forces appeared balanced. Even time itself was assumed to treat past and future equally. Reality looked orderly, almost polite. Classical mechanics exhibited beautiful symmetries. Newton's laws worked identically whether time flowed forward or backward. Spatial rotations and translations left physical laws unchanged. The conservation of energy, momentum, and angular momentum all emerged directly from symmetric principles. This success reinforced the conviction that symmetry was not just useful, but fundamental. Every new discovery that revealed additional symmetries strengthened the belief that nature operated according to perfectly balanced principles. The universe seemed to respect fairness at every level. But hidden within that order was a fragile assumption that nature cared about fairness, that what could happen in one direction must also be allowed in the opposite. That balance was not just common, but fundamental. This assumption was so deeply embedded in physical thinking that it became invisible. Scientists built theories on presumption that symmetry was inviolable, that any apparent violation must be due to incomplete understanding or experimental error rather than genuine asymmetry in nature itself. The possibility that the universe might fundamentally prefer one configuration over another seemed philosophically troubling, almost arbitrary. How could nature choose sides without some deeper principle dictating that choice? The first cracks appeared in places no one expected, not in motion or gravity, but in the behavior of the smallest particles. Certain processes work one way, but not the reverse. Mirror images failed. Time-reversed events refused to occur. These anomalies emerged from experiments with subatomic particles, particularly in weak nuclear interactions, where particles decayed in ways that violated expected symmetries. When physicists examined the mirror image of certain particle interactions, they found that nature did not produce the mirror version. When they mathematically reversed time in their equations, the predicted reverse process simply did not happen in reality. These were not subtle statistical biases that could be dismissed as noise. They were clear, reproducible violations of symmetries that everyone had assumed were sacred. These were not measurement errors. They were repeatable, consistent, real, and they suggested something deeply unsettling. Nature was choosing sides. Multiple independent laboratories confirmed the same asymmetries. Different experimental approaches yielded identical conclusions. The violations appeared in specific, predictable ways that could be incorporated into theoretical frameworks. This was not randomness or chaos, but structured, lawful asymmetry. The universe was not simply indifferent to certain symmetries. It actively violated them in consistent, repeatable patterns. This realization forced a profound reckoning with assumptions about fairness and balance in physical law. This asymmetry was not loud. It did not shatter equations. It whispered through rare interactions, subtle decays, and improbable outcomes. Easy to miss, impossible to ignore. The violations occurred primarily in processes involving the weak nuclear force, which was already the least understood of the fundamental interactions. The effects were small enough that they could easily have been overlooked if experiments had been slightly less precise. But once detected, they could not be dismissed. They appeared consistently across different particle types, different energies, different experimental conditions. The asymmetry was woven into the fabric of nature itself, not imposed by external conditions or limitations. Because once symmetry breaks, consequences follow, direction appears, history emerges, the universe gains a preference, and from that preference, everything else begins to unfold. Broken symmetry creates distinctions where none existed before. It establishes preferred outcomes, dominant configurations, and irreversible processes. Time acquires an arrow, pointing from past to future. Space develops inhomogeneities that allow structure to form. Particles gain the ability to evolve in specific directions rather than remaining locked in perfect balance. The breaking of symmetry is not destructive but generative. It opens possibilities that perfect symmetry would forever prohibit. At first, physicists resisted this idea. Symmetry was too useful to abandon. It organized laws, simplified equations, and revealed hidden connections. Breaking it felt like admitting imperfection at the heart of reality. The resistance was not merely emotional or aesthetic, though those factors played a role. Symmetry principles had proven extraordinarily productive in guiding theoretical development. They constrained possible theories, making some mathematical structures more plausible than others. They revealed relationships between seemingly unrelated phenomena. Abandoning symmetry as a fundamental principle felt like losing a compass that had reliably guided physics for centuries. Without symmetry as an organizing principle, how would physicists know which theories to pursue? What would replace it as a guiding light? So the early asymmetries were treated as curiosities, rare exceptions, statistical flukes confined to obscure experiments. Surely, deeper rules would restore balance. Surely, nature would reveal a hidden symmetry waiting beneath the surface. Perhaps the observed violations were artifacts of incomplete theories, limitations that would disappear once a more comprehensive framework was developed. Perhaps there were additional dimensions or hidden variables that would restore perfect symmetry, if only they could be properly accounted for. Scientists search for ways to preserve symmetry by expanding their theoretical frameworks, adding complexity to avoid the simple conclusion that symmetry was genuinely broken at a fundamental level. But it never did. As measurement improved, the violations became clearer. Certain particles decayed differently than their mirror versions. Processes ran forward in time without an equivalent backward version. Even when the equations allowed symmetry, reality refused to follow it. Advances in particle accelerator technology and detection methods removed any lingering doubt about the reality of these asymmetries. The violations were not borderline effects hiding in experimental uncertainty. They were robust, observable features of nature. Particles with opposite properties did not behave as mirror images. Time reversal symmetry was violated in specific, measurable ways. The more precisely physicists looked, the more undeniable the asymmetries became. Nature was not preserving perfect symmetry through some clever hidden mechanism. It was genuinely, fundamentally asymmetric. This created a deep conflict. If the fundamental laws were symmetric, why weren't the outcomes? Something was missing. Either the laws were incomplete, or symmetry itself was not as sacred as everyone believed. This conflict exposed the tension at the heart of physical theory. The mathematical structures describing fundamental forces often exhibited perfect symmetry, yet the actual behavior of particles and fields did not. Were the equations wrong, or was the interpretation of what they meant incorrect? Perhaps symmetry was a property of laws in isolation, but not the universe as a whole. Perhaps the way symmetry broke was itself governed by laws, making asymmetry as fundamental as symmetry itself. The tensions sharpen when scientists realize the implications. Without broken symmetry, the universe would be sterile. Matter and antimatter would cancel perfectly. No stars would form. No chemistry would survive. No history would unfold. This was not mere speculation, but direct logical consequence. In a perfectly symmetric universe, every particle of matter would have been matched by an antiparticle, and they would have mutually annihilated, leaving only radiation. No atoms would exist, no molecules, no structure of any kind. Even time would lose its directional character, eliminating any meaningful notion of cause and effect. The universe would be uniform, unchanging, empty. Everything that makes existence interesting, complexity, structure, evolution, consciousness, depends absolutely on the breaking of perfect symmetry. Symmetry breaking was not a flaw. It was a requirement. This inversion of perspective transformed how asymmetry was understood. Rather than being an embarrassing imperfection that marred an otherwise perfect cosmos, broken symmetry was revealed as the essential precondition for existence itself. The universe could not afford perfect symmetry if it wanted to contain anything beyond uniform radiation. Asymmetry was not nature's failure, but nature's choice, the mechanism by which potential became actual and possibility became reality. Without it, nothing would ever happen because all possibilities would remain perfectly balanced, canceling each other out indefinitely. This reframed the problem entirely. Nature was not failing to uphold balance. It was deliberately violating it, just enough to allow structure, complexity, and direction to emerge. Perfect symmetry would have been simpler, but it would also have been empty. The violation of symmetry was not random but precise, breaking some symmetries while preserving others. The universe exhibited a kind of selective asymmetry, choosing which balances to maintain and which to disrupt. This selectivity suggested that the breaking of symmetry was itself lawful, governed by principles that physicists were only beginning to understand. The challenge was to comprehend not why symmetry broke, but how it broke in such specific, consequential ways. What looked like disorder was actually permission for one outcome to dominate another, for time to move forward, for the universe to remember its past. Asymmetry granted the universe a kind of freedom, the ability to evolve irreversibly from one state to another. It allowed initial conditions to have lasting consequences, creating genuine history rather than endless oscillation between equivalent states. It permitted the accumulation of complexity over time, the building of structure upon structure in ways that perfect symmetry would forever prevent. What appeared as imperfection from the perspective of mathematical elegance was revealed as creative capacity from the perspective of cosmic development. The refusal of perfect symmetry was no longer an inconvenience. It was a reason anything exists at all. This conclusion represented a complete reversal of initial expectations. Symmetry had gone from being the foundation of physical law to being a special case, a limiting condition that reality transcended in order to produce the rich phenomenology of the actual universe. The deepest truth was not perfect balance but productive imbalance, not sterile order but fertile asymmetry. The conflict deepened when scientists traced asymmetry all the way back to the beginning of the universe. In the earliest moments after the cosmos formed, conditions were nearly uniform. Matter and antimatter were created in almost perfect balance. Energy was evenly distributed. Symmetry reigned. The universe began in a state of extraordinary symmetry, with fundamental forces unified and conditions nearly identical everywhere. As the cosmos expanded and cooled from its initial state, it underwent phase transitions during which symmetry spontaneously broke, much like water crystallizing into ice with its characteristic lattice structure. These symmetry-breaking transitions shaped the fundamental character of physical law as we now observe it. But almost was not enough. A tiny excess of matter survived. One particle for every billion pairs. An imbalance so small it seemed insignificant. Yet, that single deviation determined everything. Galaxies, stars, planets, life itself. This minuscule asymmetry between matter and antimatter is one of the most consequential facts about our universe. For every billion particle-antiparticle pairs that annihilated each other, leaving behind only radiation, one particle of matter remained. This leftover matter is everything, all the atoms in all the stars, planets, and living beings that have ever existed. The exact mechanism that produced this tiny excess remains an active area of research, but its consequences are undeniable. Without this minute violation of matter-antimatter symmetry, the universe would contain nothing but light. This buildup revealed a brutal truth. The universe does not need large biases to change direction. Microscopic preferences can scale into cosmic consequences. Symmetry breaking does not shout. It accumulates. Small asymmetries compound over time and scale, producing dramatic effects at macroscopic levels. A tiny initial preference becomes amplified through cascading processes, each building on the last. This is how minute quantum asymmetries can determine the large-scale structure of the universe. The principle extends beyond cosmology. In many complex systems, small symmetry violations lead to large-scale order. This sensitivity to initial asymmetries makes the universe far more interesting than it would be if only large, obvious imbalances could produce significant effects. As this understanding matured, it reshaped how laws were viewed. Symmetry was no longer a guarantee. It was a starting point, a fragile state that reality inevitably disrupted. Physicists began to see symmetry as an unstable condition, something that might exist in isolation or under special circumstances, but that nature tends to escape from. The ground state of the universe, the configuration it naturally settles into, is not the most symmetric state, but a broken symmetry state that permits complexity. Laws might be formulated symmetrically, but their solutions need not be. The universe operates not in the abstract space of perfectly symmetric equations, but in the concrete space of actual configurations that have definite properties and orientations. Emotionally, this was unsettling. It suggested that existence rests on accidents, on tiny irregularities that could have gone the other way, that nothing about the universe was inevitable. The contingency implied by symmetry breaking challenged notions of cosmic purpose or necessity. If slightly different initial asymmetries had occurred, the universe might have evolved in radically different ways, perhaps becoming inhospitable to any kind of complexity. The fact that we exist seems to depend on precise but apparently arbitrary violations of symmetry, rather than on some deep necessity. This contingency felt uncomfortable to those who hoped physical law would explain why the universe had to be the way it is. Yet physics showed that these breaks followed rules, not arbitrary chaos, but structured violation. Certain symmetries broke, while others survived. The universe was selective. While individual symmetry violations might appear contingent, they occurred within frameworks that themselves obeyed laws. The breaking of symmetry was not random, but followed probabilistic patterns governed by the underlying physics. Some symmetries proved more robust than others. Gauge symmetry, for instance, remained intact while playing crucial roles in modern physics. The universe exhibited a hierarchy of symmetries, with some fundamental and others emergent, some preserved and others spontaneously broken. Understanding this structure, which symmetries survive and which break under what conditions, became central to modern theoretical physics. By this point, symmetry had transformed from an ideal into a tool, something to be tested, not assumed. Nature allowed balance, but it never promised perfection. And it was that imperfection that drove everything forward. Symmetry became a hypothesis to be checked rather than an axiom to be assumed. Physicists learned to ask not whether nature exhibits symmetry, but which symmetries it exhibits and under what circumstances. This more nuanced approach proved more productive than dogmatic insistence on perfect balance. The interplay between symmetry and its breaking became a source of insight rather than embarrassment, revealing the mechanisms by which the universe generates its remarkable diversity from simple underlying principles. The climax of this story is not about imbalance as a mistake, but imbalance as a necessity. Nature refuses perfect symmetry because perfection leaves no room for anything to happen. This realization represents a culmination of decades of theoretical and experimental work, revealing that asymmetry is not nature's flaw, but nature's strategy for creating a universe capable of supporting complexity, structure, and evolution. If every process had an equal mirror, nothing would progress. If matter and antimatter were perfectly balanced, the universe would dissolve back into light. If time treated past and future the same, there would be no memory, no cause, no history. Symmetry would freeze reality in place. Perfect balance means perfect stasis. With no preferred outcomes, no processes could run to completion. With every action matched by an equal and opposite reaction at every level, nothing could build, nothing could grow, nothing could change in any meaningful way. The universe would be trapped in a state of eternal equilibrium, unable to develop or evolve. It is precisely the breaking of this equilibrium that allows reality to unfold in time, to develop structure, to generate novelty. By breaking symmetry, the universe creates direction. It allows one outcome to dominate another. It permits decay, growth, and evolution. It gives time an arrow and events a sequence. What feels unfair is what makes existence possible. Asymmetry establishes gradients that drive processes forward. It creates differences that can be exploited to do work, to build structure, to organize matter and energy into increasingly complex configurations. Without broken symmetry, there would be no irreversibility, and without irreversibility, there would be no meaningful distinction between past and future. The universe would lack the temporal structure necessary for causation, for memory, for anything resembling history or narrative. This realization reframed how physicists interpret laws. The deepest rules are often symmetric, but the universe does not stay there. It falls out of balance deliberately, settling into states that allow complexity to survive. Order emerges not from perfection, but from selective violation. The laws themselves may be elegant and symmetric, but the solutions to those laws need not be. Just as a perfectly symmetric pencil balanced on its point will inevitably fall to one side or another, the universe transitions from symmetric initial conditions to asymmetric final states. This transition is not a failure of the laws, but their fulfillment. The laws permit and even encourage symmetry breaking as the mechanism by which potential becomes actual. This insight echoes everywhere. In chemistry, where molecules favor one orientation. In biology, where life chooses asymmetry to function. Even in human perception, where perfect balance feels artificial. Nature consistently favors slight imbalance over sterile order. Biological molecules exhibit hand-deadness, with life preferring one mirror form over another. Organisms develop asymmetric body plans that enable specialized functions. Even aesthetic judgment tends to find perfect symmetry less interesting than near symmetry, with subtle variations. At every level of organization, from subatomic particles to living systems to human artifacts, asymmetry proves more functional and generative than perfect balance. This universality suggests that the principle extends beyond fundamental physics to characterize complexity and organization more broadly. Today, this refusal of symmetry continues to shape reality. It explains why the universe has more matter than antimatter, why time moves forward, why structure persists instead of canceling itself out. The universe is not broken. It is biased, just enough to exist. Every atom and every star owes its existence to the tiny matter-antimatter asymmetry that emerged in the early universe. Every moment of experience depends on time's arrow, itself a consequence of broken symmetry. Every stable structure, from crystals to galaxies to living cells, exists because asymmetric configurations are energetically favored over perfectly symmetric ones. The cosmos we inhabit is fundamentally a broken symmetry universe, and that breaking is what makes it capable of containing observers who can reflect on these questions. Perfect symmetry is elegant, but it is also empty. And nature, it turns out, prefers a universe that can happen. This preference is not arbitrary aesthetic choice, but physical necessity. A universe with genuine content, with structure and complexity and capacity for interesting phenomena, requires broken symmetry as its foundation. Nature's refusal of perfect symmetry is what transforms possibility into actuality. What allows a universe to be not merely conceivable but actual, not merely order but alive with creative potential. Why